Okay, hi guys, I'm Kelly Ellis, if you didn't already know me, and today I'm going to be talking about Hellenistic optics in music. So just a little overview of what I'll talk about today. We'll start with Euclid, and then we'll go into Diocles, Heron, and then Ptolemy, and we'll talk about their works with the optics and like what they proved and how they made their mark on this topic. And then we'll go into the music, which I know it kind of sounds weird in a history of math class. We're going to be talking about music, but we'll see how it kind of connects later on in the presentation. So first, we're going to start with Euclid. So Euclid was a Greek mathematician, and he was often referred to as father of geometry and then also founder of geometry. So one of his books is entitled Elements, and it's actually one of the most influential books in mathematics, like in the history of mathematics. It actually serves as one of the main textbooks that people use for teaching math, and especially for geometry purposes. So in this book is Euclid's geometry, where he deducts theorems and he has a small set of axioms that he shows. And he also wrote about like conic sections, spherical geometry, number theory, and a number of different things. And he also has his work with Euclidean optics, which we'll actually see right here. So Euclid's Optics is actually a work on the geometry of vision, which he wrote around 300 BC. It's actually one of the earliest surviving manuscripts of optics that is written in Greek. So that's very interesting as well. He was kind of a pioneer for this. But the work mostly deals with the geometry of vision rather than physical and psychological aspects of sight, which you'll see from other people before him as well as after him that works in this topic. So no scientist actually has given this much thought and attention to this topic for Euclid. So like I said, he was kind of a pioneer for this. But in his optics, he begins with a small number of definitions and postulates, and then he proves by deductive reasoning different geometric propositions. One of the things he actually talks about is that eyes see objects in a visual cone. So we kind of see here in this image what he was kind of referencing there. And we'll kind of see later on really what that means and how other people interpreted that and got proofs from it. So one of the things that is important with Euclid's optics are his postulates. So later on we'll prove, actually on this next slide, we'll see one of the proofs that Euclid did. And all of his proofs were based off of his postulates that we see here. I'm not going to read them off to you because it is a lot, but well, there's 7 of them. And as you see, the seventh one says that things seen under more angles are seen more clearly. And that makes sense, of course, because if you're seeing an object or something on multiple angles, you're going to be able to see it more clearly and really get the dimension and just the details that are in that rather than just one angle, because you won't be able to see the entire thing. So taking those, we can kind of see one of his proofs. So there was a number of different proofs that he has done because he is so influential in this area. But this is the one I chose to kind of talk about. So this is saying, this is what he's proving. He's proving that rectangular objects, when seen from a distance, appear round. So we kind of have this picture that we were referenced up here. So we see this rectangle. And so this is how the proof went. So he said for rectangle BG, which we see here, standing upright, it can be seen from a distance. Now, since each thing that is seen has a certain limit of distance beyond which is no longer seen, the angle G is not seen. So kind of what we were talking about earlier is like the different angles. You're not going to be able to see everything unless you have each viewpoint. And then it goes on, but only the points D and Z are visible. So we see DZ here. Those 2 points are going to be visible, but not G whenever you're standing from a certain distance. And then it goes on in the same way also in the case of the other angles, this will happen. So if we apply it to each of the other corners that we see there that we didn't talk about, it's going to be the same case. Those 2 points are going to be able to be seen whereas these corner points where like G is and B, they're not going to be as visible. So that leads to our conclusion that the whole thing will appear round, which is kind of weird to think about in like how our eyes depict things, but he ended up proving that yes, rectangular objects, when they are seen from a different distance and farther away, they're going to appear round, which I guess you could probably like test that as well, like seeing a rectangle and then backing up, you're not going to be able to see those sharp, crisp corners, and it's going to look round. So that was all for Euclid. Of course, he did a lot more, but we have to talk about Diocles and his optics. So Diocles had a work that was entitled On Burning Mirrors, which we'll see later, but he was a Greek mathematician and a geometer, but little is really known about him because a lot of his works is missing and not really documented as heavily as the other ones. But for, oh yes, and he was the first person to prove the focal property of the parabola. And so we have kind of seen that a little bit and in our work with geometry and the foci and the different axes. But he also had this work on burning mirrors, and it was a large influence on Arabic mathematicians. It contained 16 different propositions, which I did not include because that was a lot, but that's what he used in order to prove different conic sections. So he proved a lot from that, but he described what was known as a spherical aberration. And so that is like something that's unwanted. So let's simplify that a little bit. So basically the problem was that light rays fall on a lens and different rays don't meet after the lens in a single focal point. So any imperfections in that lens is going to prevent the removal of that aberration. So any little specks or anything that might be on the lens, even if it's the most high-end model, you're not going to be able to remove all those unwanted, it's not going to be that as crisp. So, I mean, I feel like that makes sense in what we think about that as well. So Diocles brought up the problem that this problem, and no one really has been able to come up with a good final answer to it. So even with all of our work in cameras and vision and stuff like that, no one has been able to come up with a good, like universally collected solution to these problems that he raised, that's really saying something since so much work has been done here. But this is kind of what I just went over. But yeah, so nobody in history is able to find a good answer for these problems, which is quite crazy just with all the work that we have done with this topic and in our camera work and how much it is advanced from the time of Diocles and Euclid and the people before us. So now we'll move on to Heron. So he was actually also called a hero of Alexandria, but he was often considered the greatest experimenter of antiquity, and his work is representative of the Hellenistic scientific tradition. He is one of the greatest experimenters. So he came after Euclid, but he did a lot of work in which we'll see optics, and then he has his book Machines and Optics. But he formulated the principle of the shortest path of light. So he basically said that if a ray of light propagates from one point to another in a same medium, then that path length is the shortest path possible. So this was, of course, built on in later years, and we actually, this is what's known as that the optical path is stationary. So that's where it kind of like developed into, and that work got onto that. So our next person is Ptolemy. And so Ptolemy, he was a mathematician, astronomer, geographer, and astrologer. So he kind of dipped into a lot of different things, and I feel like he's pretty well known for his works. But his work actually only survives in poor Arabic translation, and in about 20 manuscripts of Latin version of the Arabic. So like him before, his optics is poorly translated and poorly kept up, so we don't know too much about him, just like our last person. But he dealt with the properties of light, so that's reflection, refraction, and color. So I kind of put this picture here, but like that's what he was kind of dealing with, and the idea of the properties of light. So he did a lot of work with that, and he had a significant part in the early history of optics, and he actually ended up influencing a lot of the more famous books, like the Book of Optics. But it contained the earliest surviving table of refraction from air to water, and it was historically really praised and experimentally derived, and it really came from this arithmetic progression. So now we'll go into like perception. So he was super important for the early history of perception, and he dealt with the extramission and intramission theories of vision. So that's where like the rays from the eye formed a vision, and the vertex being within the eye, and the base was defining the visual field. So the rays were sensitive, and it conveyed information into the observer's intellect about the distance and the orientation and just the perception of what we see. So size and shape, though, were determined by the visual angle, and it was attended at the eye combined with the perceived distance orientation. So this was one of the early statements of size, distance, and variance as a cause of the perceptual size and shape constancy, which was supported by later researchers and scientists. But Ptolemy offered explanations for many of the phenomena that concerns illumination and color, size and shape, movement, and binocular vision. He divided these illustrations into those that were caused by physical or optical factors, and then also by those that were caused by judgmental factors. So he often offered an obscure explanation of the sun or moon illustration. So he based this off of the difficulty looking upwards, like looking up at the sun and the moon is not super easy, but he was able to do an enlarged apparent size on the horizon and give an explanation for the sun and moon illusion that we like see whenever we think about those and look up, because it is so hard. Okay, so now we get into music. In music, I kind of connected more to Ptolemy, but we'll go into him and what really this means for music. So Ptolemy wrote an influential work which is entitled Harmonics, and this was on music theory and then also the mathematics of music. So like that kind of sounds weird, but mathematics of music, I'm not a big music person. But I relate to this mathematics, so I was very interested to see what exactly music had to do with our subject in our class. So Ptolemy criticized the approaches of the people that came before him and worked on this stuff, and he argued that he argued for basing musical intervals on mathematical ratios. So he kind of argued for these music intervals should be in a certain ratio, and that's how they're depicted, which was very interesting to see and learn about. But all of that was backed up by his empirical observation that he had done. He also wrote about how music notes could be translated into mathematical equations, and then also vice versa in harmonics. So this was called Pythagorean tuning because it was actually first discovered by Pythagoras. But the difference is Pythagoras believed that the mathematics of music should be based on a specific ratio of 3:2, whereas Ptolemy, he merely believed that it should just be generally involved the tetrachords and the octaves. So they kind of varied on that. That's why it is referred to as the Pythagorean tuning, but it did have some differences on what Pythagoras had thought about that topic. So he ended up presenting his own divisions of the tetrachord and the octave, which he derived with the help of a monochord. So it was kind of interesting to hear about how they took music and translated it into mathematics and ratios and equations. It just really made me rethink about the topic and how so many things can come back to math and how interdisciplinary it can be. So that is all for today. These are my sources, and I hope you guys learned something new about optics and music, because I definitely did whenever I was researching this, because this is not something that I have learned about or heard about in any of my classes. So that is all.